So we've examined how you can look at the different values of the y-hats, the residuals, and these correlations. They have particular properties as a consequence of minimizing the sum squared errors. And we can use these properties to have a decomposition of the variation or outcome. And from this decomposition of the variation or outcome, we can derive measures of fit. So we can say, well, the least squares line may fit a data not so well, may fit the data very well. And we can create what we call diagnostic measures of fit. So recall that for our raw values, we can decompose every observation, every row of our data set in terms of that part which is explained by our input variable, the y-hat, and that part which is unrelated to our input variable. That's the error, that's the residual. Because the correlation between our fitted or predicted values of our outcome and the residuals, because that correlation is zero, because they're not related, we have a very easy way of decomposing the variation in our outcome. And we can say that the variance of y, meaning the variation, the total variation of our outcome, can be split up into that variation which is due to the fitted values and that variation which is due to the errors or residuals. To put it another way, the variance of y equals the variance of y hat plus the variance of our errors or residuals. If the correlation between the y hats and the residuals, if it weren't zero, then we wouldn't be able to make this very clean distinction and this nice decomposition. So we can rewrite our decomposition of the variation or outcome in terms of this formula. Right? This is simply the variance of y equals the variance of y hat plus the variance of our errors. And we're using, if you recall the variance, we use the mean of a variable as the benchmark. And so we're looking at all the distances for the total variation. We're looking at the distances of the raw values of y around the mean of y, and we're squaring those, and we're calculating what's an essence and average, all right, for these squared, sum of squared deviations. And for the y hats, right, the variance of the y hat, we're still using the mean of y as our benchmark. And then we can also calculate the variance of the errors or residuals. When we decompose the variation this way, we can talk about the total sum of squares, the model sum of squares, and the residual sum of squares, or sometimes it's called the sum of the squared errors. Right? We've seen the sum of squared errors before. This is sometimes called an analysis of variance, because what you're doing is you're partitioning or splitting up the total variation of the outcome, the total sum of squares, into that part which can be accounted for by our model and that part which can be accounted by the residuals or the errors. So we have that sort of variation which is from our model and that variation which is not due to our model. So it's useful to look at a particular observation to really understand what's going on here. So here I've labeled the total sum of squares equals all those raw values of y around the mean of y. And you square them, add them up, so they're all positive. You can also think of variation due around the actual y hats. So if you take the raw values of our outcome and you subtract out the y hats, these conditional means, right? You get, and you square them so they're all positive, you add those up, you get the sum of the squared errors. And then you have the model sum of squares. Those are the y hats, those fitted or predicted values around the mean of y. And when you square those and add those up together, we get the model sum of squares. So any particular observation for any particular value of x in our data set, you can say, well, you have that raw value of y, but you can split that raw value of y into that part which is due to our model, the y hat, and that part which is unrelated. That's the error, that's the residual. So the mean of y is our benchmark here. And we have a y hat, and then we also have a raw value of y. Okay, so for any particular value of x, we have a raw value of y, we have the predicted value or the expected mean based on that value of x, and then we have the overall mean of y, which is the same for all observations. And from this decomposition of variation, we can calculate something called the coefficient of determination. Right? This is called r squared. What this does is it tells us the proportion of the variation or outcome accounted for or explained by our model. R squared is simply the model sum of squares divided by the total sum of squares. So the total sum of squares, that is all the variation of our raw values of our outcome around the mean of our outcome. The model sum of squares, that is all the variation of our raw values of the outcome around, or rather our y hats around the mean of y. So the model sum of squares is the y hats around the mean of y, and the total sum of squares is the raw values of y around the mean of y. And this value that we call r squared, it can also be calculated by taking 1 minus the sum of squared errors divided by the total sum of squared errors. Conceptually, the r squared value can range from 0 to 1 inclusive, and it tells us the proportion of the variation in our outcome that is accounted for or explained by a regression model. That's because it's a fraction, right? If the model sum of squares, right, that captures the amount of variation in our outcome that is accounted for, explained by our model. So if the model sum of squares explains a big proportion of the variation, right, then we can say that this model is doing a pretty good job of fitting to this set of data. Right? A related measure is something called the coefficient of alienation. I like it because it sounds cool. It's 1 minus r squared. And it's sometimes known as a coefficient of non-determination. It's not commonly reported, but it is a similar measure. It measures the proportion of the variation outcome that is not accounted for, not explained by the variables in our model, by those variables on the right-hand side of the equation. So in a simple linear regression model, we have one input variable, one x variable. So it tells us how much variation in our outcome is not accounted for by this x variable. Right? And sometimes it's useful for examining what we call multicollinearity in regression models. We will talk about this idea of multicollinearity near the end of the semester when we revisit regression analysis. For our purposes today, you can think of r squared as the proportion of the variation in our outcome accounted for by our model, and that's the model sum of squares divided by the total sum of squares. And when you take 1 minus r squared, you get the proportion of the variation in our outcome that is not accounted for or explained by our model. A related measure besides r squared is something we call the root mean square error. Well, what is the root mean square error? Well, this is one of the beauty of statistics, is that the terminology in statistics tries to be as clear as possible. So what is the root mean square error? It's simply the root mean square error. It's sometimes called the root mean square deviation. Conceptually, what it is you take the sum of the squared errors, you divide by what is effectively the degrees of freedom. Right? You're basically calculating an average. And then you take the square root to undo the squaring. And the root mean square error, what it does is it gives you an idea of how good your model is at predicting. Right? The root mean square error gives you an idea of, on average, how large is one of those errors, one of those residuals going to be. So if you have a fairly large root mean square error, that suggests your model isn't that great at predicting. If you have a small root mean square error, it suggests, on average, your model is going to be pretty close, right, to the raw value. Right? So the root mean square error gives you an idea of, on average, what is the size of the error or the residual. Right? Smaller root mean square error, you're doing a better job of predicting values. A larger root mean square error, your model probably isn't as good as predicting. So let's look at Galton's findings again. So the r squared from our model, that is the model sum of squares divided by the total sum of squares, is about 0.1058. So that tells us about a little over 10% of the total variation in heights among children is accounted for by the height of their parents, which may not seem like that large of amount. It suggests that there's a lot of other causes, potentially, of variation among heights of children. Nutrition might be another one. You might have other genetic causes. The other factor is the root mean square error. The root mean square error for a model is 3.39 inches. So it suggests that on average, we're off by about 3.39 inches when we use our model for prediction. So if I tell you, if somebody asks you, what is the predicted value of children's height if x equals 100? Well, you're going to be off on average by about 3.39 inches, either above or below the actual, in terms of the y hat. The raw value of y you'd expect to be above or below 3.39 inches. That's pretty good, I would say. So you can see that r squared and root mean square error, they're related in the sense that, the basic idea is they're both giving you measures of model fit, but they are different concepts. R squared gives you an idea of the total variation that is accounted for by your model. Root mean square error gives you an idea of, on average, the size of that deviation. right? So let's look at another example of heart rate and exercise. So suppose you're trying to predict heart rate based on hours of exercise, and you obtain some data and you grab this result, okay? This is the output from a statistical model, and so we're predicting the pulse rate per minute based on exercise. So we get these coefficients, these values of the intercept and slope using the method of least squares. The intercept is about 69.7, right? So in exercise, when that value is 0, when that variable is 0, we get an expected mean of 69.7 beats per minute. The slope, it tells us for every 1 unit increase in our x variable, we'd expect the value of our outcome to decrease by 0.12. That tells us that there's probably a negative linear relationship, which makes sense. The more you exercise, the lower your heart rate per minute. This is what the slope looks like. This is the actual scatter plot of our data set. So we have this simple linear regression model. We can see we have a negative slope, suggesting a slightly small, a slight negative linear relationship. Now we might ask, is this fitting the data well? We do know that this line is based on the minimum sum of squared errors for this particular scatter plot. Any other line will have a larger sum of squared errors. We might ask, is it doing a good job fitting the data though? Well, let's look at some measures of fit. The R squared from this regression model is 0.0097, right? That suggests it's accounting for less than 1% of the total variation in heart rate by this variable of how many hours you exercise. So it's not explaining very much of the variation or outcome. So we might suggest we might try a different variable. Maybe there's something about our hours exercise variable that is, it's not very predictive. It's not a good input. Maybe we want to look at nutrition variables. Maybe it's the kind of exercise. Maybe it's based on self-report. So people are just saying they exercise a lot when in fact they don't. So there's something about this variable that's suggesting maybe it's not the best input for this regression model because it's not accounting for that much variation in pulse rate. The root mean square error for a model is about 10. So that suggests on average, if we use this model for prediction, we're going to be off by about 10 beats per minute, right? So overall, we might conclude this is a rather poor fit. We might look at a different variable as an input into this regression model. So things to know about decomposing variation and measures of fit. We can decompose the variation in the outcome into that which is accounted for by our input variable, it's accounted for by a model, and that which is unrelated to our model. So we have the fitted part and the error or the residual part. And we can even say that the total sum of squares, okay, equals the model sum of squares plus the sum of squared errors. And then we can use this decomposition of the variation to calculate a measure of R squared and the root mean square error. The R squared is simply the model sum of squares divided by the total sum of squares. And we can use these tools to gauge the overall fit of our regression line to a scatter plot of data.